I think we should start. The time has come. It's inevitable. Who had a good sleep? Come on. Literally, no one? Okay. Who'd rather to stay sleeping at home? Okay. At least you are honest. Well, as usual, at the beginning, I should say some inspirational speech. Oh, it's a tradition. So, welcome to hell. This is the best way how I can describe the algebra. So, why is this? Well, first of all, I know who your lecturer is. So you will be suffering. So the suffering and misery will be your best friends during these 10 weeks. The second, hear my accent, so your ears will be bleeding during the lecture and the seminar, so that's fine. That's totally planned. And the third reason, algebra is the best way to make fun of students. So I'm not going to resist the temptation. You have been warned. Okay. Now, my name is Dima. Well, first of all, I have to explain how everything is organized here, how you will get your final grade, and then we will do the real stuff. Regarding your grade, so we will have, it's hard to remember all of these numbers. Yeah, so regarding about the grade. We have homework. So each week you will get 4 problems to solve. We will have approximately 9 homeworks. And the coefficient is 0.3. Then we will have a written test. It will be somewhere at the end of the module, and probably after the 9th lecture. So, what is the test? During the test, we want to test whether you know how to solve problems. So this will be written tests, 0.3, and at the end, we will have an exam. This will be an oral exam, 0.4. And during the exam, we will check whether or not you know the theory. So here and here, you will learn how to solve problems, and here you will show how you know the theory. So these are all the components that we have, and if you add them all together, you will get your final grade. Okay, so this is the formal stuff. Now, I believe at the end of this week, there will be a wiki page containing all the information regarding the course. There you will find like the list of topics for the lectures, and you will find the lecture notes. So after each lection, I will post the lecture notes on the wiki page. Yeah, if you want to contact me and ask any question regarding the course, you may write me via Telegram. It's not very hard to remember. This is my nickname. What else? Oh, yeah. Now, one final thing before we start. Okay. Let me tell you why I'm here. The reason why I'm here is not because I have to teach you algebra. The reason why I'm here is because you came here. And if you came here, it means that you want to learn something. And my duty is to provide you some accessible knowledge. So if you have any questions, if you don't understand something, if something wasn't clear, don't hesitate to ask questions. I mean, the most dumbest question that you've ever heard is the one you never asked. I mean, if you don't ask questions, you will never learn something. And today I have a special guest here to help you to ask questions. Let me introduce this guest. Here it is. His name is Lasyash. So what is the role of Lasyash? If you don't understand something and you don't ask a question, he will burn you with shame. Because literally, look at the eyes of this guy. He's really tough. So yeah, if something is not clear, just ask a question. And yeah, and if you don't care about the algebra, if you don't care about the grade and you just want to pass the course, I mean, I don't care if you come here or not, it's up to you. So, I mean, if you don't want to learn this, everything you have to care about is this thing. So you just need to get some, 4 scores as your final grade, and that's it. But if you come here, I assume that you want to learn something, so that's it. Okay, I believe this is all that I wanted to tell you before we start. Are there any questions before we start?
Is the examination blocked?
No, there are no blocking elements of control. I hate blocking elements of control. I mean, they serve no purpose. They are absolutely useless and Okay. Are there any other questions?
How often do we get our homework?
What again?
How often do we get homework?
Every week after each seminar. And the deadline will be the next seminar. The deadline will be strict. The reason for this rule is simple. Well, after each homework, it will be useful to discuss with the seminarist your homework. So if the deadline is not strict, then you can do this, because other people may solve at home during this. The deadline will be strict. Let's start. So what is algebra? Well, in algebra, we study algebraic structures. What is an algebraic structure? Well, basically, algebraic structure is a set with a bunch of operations. So we want to start with the simplest case, is a set with one operation. And it will lead us to the notion of a group. So let's start step by step. First of all, a binary operation. So what is a binary operation? Well, suppose we're given a set. A binary operation, well, is a map. So a binary operation on the set X is a map with this signature. Just in case, who thinks that he understands what's written here? Who thinks that what's written here requires clarification? Okay. Okay, just in case. So this is the source. We take a pair of elements from X, and we produce a new element, and the name of the new element is xy, and the operation is between x and y. So this is a binary operation. What examples of binary operations? Well, we have a lot of different binary operations. Just in case, the simplest ones, you can take the set of integers, then you have addition, or you can take the set of integers with subtraction. Then you can take the set of integers with multiplication. Is it possible to take the set of integers with division? Yeah, that's right, because division is not well defined. The result of division is not integer. But what if I take rational numbers with division? Is it okay?
No.
Why?
Because there is 0.
Yep, exactly. So what are the other operations? Actually, there are a lot of different binary operations. You can take the maximum of 2 elements, the minimum of 2 elements, or any binary function you want. Literally, there are a lot of different binary operations. Now, since there are a lot of binary operations, we don't want to deal with all of them. we want to take just good binary operations. And what does it mean good? We want them to satisfy some properties. So what kind of properties? Well, I want to discuss several properties of binary operations. So the property number one will be associativity. So properties. Okay, so what does it mean that an operation is associative? So if we have a binary operation on a set X, associativity means that for any free element X, Y, and Z, well, what you can do, you can multiply X and Y and then multiply the result by Z. Or you can multiply Y and Z and then multiply the result by X. So we want this to be the same. Okay, now here we have 5 examples. How many of them are associative?
All.
Who thinks that all these operations are associative?
Not the minus.
Okay, except this one. Subtraction is not associative. These, and these 2 are associative, and this one is not. Okay, so this is associativity. So what's next? The next one, well, the existence of a neutral element. So what is a neutral element? So if we have a binary operation, then we can define a neutral element. Neutral element is a special element, let's call it E, and it satisfies the following property. For each element X, if we multiply X by E from any side, we will get the same X again. Well, it's very important to notice that in this definition, you have to formulate both properties. You have to multiply from the right and you have to multiply from the left. If you take just one of them, well, the other one may be wrong. So if you have such an element with this property, every such an element with this property is called neutral element. Okay? Now, do we have a neutral element for this operation? 0. Do we have a neutral element for this operation? No. There are no neutral elements. Why? And you see, well, if you take an element X and subtract 0, you will get X. So subtraction satisfies this equality, X times E equals X, as you can see. But there is no element Y satisfying this property. Because otherwise, Y should depend on X, but it should be some specific element independent of the choice of X. So there is no neutral element here. What about this one? 1. What about this one? But do you have minus infinity in Z? I mean, it depends on the set. Well, if you take the set of integers with minus infinity, then yes, it has. But I mean, in case of integers, max and min also do not have a neutral element. So yeah, only these 2 operations have a neutral element. Now, there is a natural question. In this definition, we say that if an element E satisfies this property, then it's called a neutral element. So it may happen that you have a lot of different neutral elements. Okay? So how many neutral elements do we have? Well, actually, at most 1. First of all, it may happen that there is no such an element, like in this case. And actually, let's say it's like the statement, if we have a binary operation, and we have two elements, E and E prime, and these are neutral elements for this operation, then E is equal to E prime. So why is that? Well, let's multiply E by E prime. Now, since E is the neutral element, if we multiply the neutral element by anything else, we will get this anything else. So this is because E is the neutral element. From the other hand, since E prime is the neutral element, if we multiply it from the left by anything else, we will get this anything else. This is because E prime is the neutral element. So that's why E and E prime are the same. And this proves that if you have at least two neutral elements, they are exactly the same. So there are only two options. We either have no neutral element, or we have exactly one. Okay, who was able to follow? Just in case. Cool. Now, the next thing to discuss is the notion of an inverse element. Well, now, suppose we have a binary operation with a neutral element. Okay? Now, I want to define an inverse element of an element x. So suppose we have an element x from x capital. Now, I will say that y is an inverse to x if x times y is equal to e and y times x is equal to e. So these two equations hold. So basically, what does it mean? It means that if you multiply your element from the left and from the right, you will get the neutral element. In this case, y is called an inverse. Well, in the world of like integers or rational numbers, if we have like or in case of matrices, if we have an inverse, it's usually unique. So let's discuss how many inverses to an x we will have. Well, in case of an associative operation, we will have exactly one inverse. Well, at most one inverse. So let's prove it. So if we have an operation, associative operation, and there is a neutral element, and it happens that we have these two equalities for x and y, and these two equalities for x and y prime. I think I should switch to a different color. This one. It's bleak. Okay. Well, in this case, if this happens, then y is equal to y prime. But this basically says if you have two elements, y and y prime, and they are inverse to x, then they are the same. So it may happen that there is no inverse, but if you have two inverses, then they are the same. And here, it's important that the operation is associative and we have the neutral element. If we do not have a neutral element, then it doesn't make sense to say that something is inverse to something. Because in order to say this, we have to use this neutral element. And without this assumption, the statement is just wrong. Okay, so why is that? Just in case. Is there anyone who knows how to prove this? Okay. The trick is basically the same as here. We should consider some expression and compute it in different ways. So let's start with this expression. Y times x times y prime. But when you have this expression, you have to tell which operation goes first. First of all, we may compute y times x and then multiply it by y prime. Go the other way around. You can multiply x times y prime and then multiply it by y. Since the operation is associative, it doesn't matter which way to choose. The result will be exactly the same. So these two expressions are the same. But let's compute the first and the second expression. Okay, if we multiply y by x, because of this property, since y is inverse to x, this one holds. So this is E, the neutral element. So here we have E times y prime. But since E is the neutral element, just by definition of the neutral element, this expression is y prime. Now, we use exactly the same logic to compute the second expression. So x times y prime, because of this, is equal to y times E. And because E is the neutral element, the result will be y. So again, following this sequence of equalities, we'll see that y prime and y are the same elements, and we're done. Okay, are there any questions, just in case? Okay, good. So now we know that in case of an associative operation with a neutral element, we have at most one inverse element. Okay, what about inverse elements here? Like if you take an element A, what is its inverse here for this operation? Okay. What if you take an element here? What is its inverse here? It's not important that it's not associative. What is important is the neutral element, so it doesn't make sense. So the question itself doesn't make sense because the preconditions for the notion of the inverse element are not satisfied. So because we don't have a neutral element, it doesn't make sense. So what about this thing? If I take an element A, what?
It's the power of minus 1 power.
These are integers. Well, actually, not every element here has inverse. So what are the elements that have inverse?
0, 1,
I almost agree with you. I don't like the element 0 in the list. Because if you multiply 0 by anything, you will get 0, and you will never get 1. So it doesn't have an inverse. So 1 and minus 1. These are the only options here. So the only invertible elements here are 1 and minus 1. Okay. What's next? Okay. Oh, yeah. Before we go next. So since we know that in this case, the inverse element is unique, we will denote the inverse element by x to the power of minus 1. So since y is unique, just in case, this exclamation mark means unique. It's just a shortening for the uniqueness. Then we will denote it by x to the power of minus 1. Well, it's just for simplicity. So we, like our brain is used to notion of an inverse number. And in case of an inverse number or inverse matrix, we use this notation. So in case of binary operation, we also stick to this notation. Well, it's very convenient. And the fourth property is commutativity. So if we have a binary operation, we will say that this operation is commutative if the order of arguments doesn't matter, which means that if you multiply x by y, this is the same as to multiply y by x for all possible elements x and y from the set x. For all possible elements. So in this case, we will say that the operation is commutative. So these are for basic properties. Okay, what about these operations? Which of them are commutative? This one. This one. This one. No, this one. Okay, good. Yeah, this one is the only exception. Okay. Now we're ready for our first serious definition, the definition of a group. Okay, before giving you the definition of a group, I want to make some general remark. Well, you will encounter a lot of different definitions in algebra or like in other branches of mathematics. And usually they follow the same pattern. So I want to show you the pattern of any abstract definition. Usually when you define something, so you want to define something, you need to provide two things. The first thing is the data. Like you have to tell what exactly you have. So what kind of object should be defined before you can check any properties or say that you have something. And then you have a list of axioms for the data. So every definition we will have during this course will follow exactly this pattern. So first of all, I have to provide you the data, and then I'll give you the axioms for the data to satisfy. And the definition of a group will not be an exception. So what's next? Oh, the definition of a group. Okay, so what is a group? I want to define a group G. Well, in order to define a group, first of all, I have to provide you with the data. So what do I have? First of all, I have a set, G. This will be the set of elements of the group. The second thing I have is a binary operation on the set G. These are all the data. So in order to define a group, first of all, you have to name explicitly the set G, and then you must be able to define explicitly the operation. But not every set and every operation form a group. Then we have some conditions for the operation, and these are the axioms. And we have several of them. The axiom number one, the operation must be associative. Just in case I will recall what it means. So it doesn't matter how you put the parentheses. The second thing, the operation must have the neutral element. There must exist E, the neutral element. Just in case I want to recall the definition of the neutral element. And then you want every element X to be invertible, in the sense that for every element X, there is this one inverse element. So for each element X, there is element Y such that X times Y equals E and equals Y times X. And again, we will call this element X inverse. So this is the list of axioms. So now, again, what is a group? The group is a set with a binary operation such that this binary operation follows these rules. Okay? Who thinks that the definition is clear? Are there any questions regarding the definition?
What is the sense of giving such definitions, like where to apply them?
What again?
Where to apply such?
What do you mean where to apply? You want me to provide an example?
Yes, please.
Yeah, the example are immediately followed. Okay, so
I mean, the example is obvious, but where can we use such definition? For example, we have proved that something is a group, and what's that?
okay, you'll see. I mean, probably during the third lecture, we will apply group theory for cryptography. Then later we will apply it to coding theory. You will see. Like, I mean, well, in general, algebra is actually the most useless part of mathematics. Like, no, really, it's the most useless part of mathematics. So that's why it's the most interesting one, but okay. But still, there are several topics in algebra which are useful in applications. And some topics are useful for cryptography. Some topics are useful to error correction codes. Some topics are useful for symbolic computations. And I'll try to cover all of these topics during our course. Okay, now, let's take Z with addition. So we have a set, and we have a binary operation. So all the data is presented here. Is this a group or not? Yes, exactly. This is a group, because the operation is associative. The neutral element is 0. And for every element A, its inverse is minus A. So this is a group. Now, what about this one? Why? Well, it doesn't make sense to say about an inverse element because it doesn't have a neutral element. So the property number 2 fails to be true. I mean, okay, and it's actually not associated. What about Z with multiplication? Again? It is a group. Okay, let's check. The third condition fails to be true, yeah. The third condition falls because we know that, for example, 0 is not invertible, and 2 is not invertible here. Okay, what if I take Q with multiplication? Is this a group? By the way, do you know the notation? Is it clear? Just rational numbers, just in case. Okay, again, this is not a group. Why? Yeah, and if I exclude the 0, it's called Q star. Yeah, if you exclude the 0, this is also a group. The neutral element will be 1. Multiplication is associative, and for each element A, 1 over A is its inverse. It's also a rational number. Yeah. Okay, so these are not groups, and these two are groups. Actually, we have some other examples. Let me give you these ones. Okay, these. Okay, yeah. So let's take Zn plus. Okay, what is Zn? Zn is the set of all remainders modular n. So we take elements 0, 1, etc., n minus 1. Okay, so this is the set. Now, what is the operation? The operation is sum modular n. So if you have two elements, x and y, from this set, so the operation is x plus y modular n. So you find the sum and find the remainder modular n, and this is the result. Okay, is this a group or not? So it looks like a group. Okay, so the operation is associative. We know this fact. Now, what is the neutral element?
The inverse modular.
What? The neutral element is 0. Yeah, okay, yeah. And what is the inverse?
N minus
And yeah, if you have an element k, then n minus k is the inverse. Except for the case k equals 0. In this case, the inverse is just 0. But yeah, so we know that how to compute an inverse element for this specific case. So yeah, this is a group.
Actually, n minus k is 0.
Formally, n minus 0 is not presented in this set. So when you define an operation, it should provide a well-defined element of the set. So element n is not here. So that's what, I mean, you can use element n to denote 0, but in this case, you somehow assume that n is just a different name for the element 0. It's convenient, and people do this thing. Like, for example, it's convenient to use notation -1 instead of n minus 1 because it's more convenient. But still, the real elements here, 0, 1, and etc., n minus 1. So there is no element -1 or element n by definition in this set. Okay, the next definition. So Zn star with multiplication. So what is Zn star? What again? No, not just 0. You take all elements from Zn such that A and n are coprime. So this is the GCD of two integers. So it means that there is no common factors between A and n. So these are coprime integers from Zn. Now, what is the operation? The operation is multiplication modular n. So if you have x and y from this set, then x times y modular n is the operation. Now, the first thing you should worry about is the well-definedness of this operation. What does it mean that the operation is well-defined? If you are given two elements from your set, the result must be inside your set. So if you are given two elements x and y from here, well, and multiply them modular n, the result is definitely here, because the result of this operation is always here. But also x and y were coprime with n, and if you multiply them, the result is also coprime with n, and the remainder will be coprime with n. So yeah, this operation is well defined. So definitely the result belongs to this set. Now, is this operation associative or not? Yeah, it's associative by the rules of remainders. Now, do we have the neutral element? What is the neutral element? Again? 1. Yeah, exactly, because 1 belongs to this set and 1 is coprime with n. So 1 is the neutral element. Now, do we have an inverse element for an element A? Well, the answer is yes, but it's not that obvious. Let me tell you why there is an inverse element. Well, suppose we have an element A here, which satisfies this property. So what does it mean that the GCD of A and n is equal to 1? We know that we can represent GCD as a linear combination of a and n with some coefficient. So from this, it follows that 1 can be presented as u times a plus v times n, where u and v are some integers. Who knows this result? Just in case. Again? Well, it's actually division with remainder. If you divide, there is an algorithm to find the GCD when you divide one element by another one, and then when you get the GCD, you can substitute all this expression the other way around, and you will get the expression for the GCD in terms of the initial two elements. Okay, just in case. Who doesn't know this result? Just, okay, if you have a question regarding this thing, we can discuss it during the seminar, but now use it as a black box if you're not sure why it's true. But now, this is equality of integers. Let's take this equality modular n. That what will we get is 1 is equal to u times a modular n, because v times n is 0 modular n. And now you see, we have found an element u such that u times a is equal to 1 modular n. And since our operation is commutative, it will be true the other way around. So, I mean, u is the inverse element for the element a. So this is how you find this inverse element. So you need to represent GCD as the linear combination of a and the coefficient near a modular n is the inverse element. Okay?
You can be not in.
What again?
Why you in this set?
Oh, why u is in this set? Because
Understand if you take this PBU modular n. Then
yeah. No, I mean, you should take u modular n.
What if this u is not coprime?
Well, if u is not coprime with n, then there is a prime number which divides u and n. Then the right-hand side is divisible by this prime number, but the left-hand side is 1, so it's not divisible. This is a contradiction. Okay? So it will be coprime. Yep. Yeah. These one and this one are the same. Yeah, because I choose this equation and I took it modular n. So this is the same equation, but I consider it modular n. So modular n, this part is 0, so we have just this one left. And this part is just a part of this equation.
You times a modular n leaves u untouched, so
Could you say it louder, because I can't hear you.
когда мы берем по модулю n, получается u на а модулю n меньше, чем на обязательно.
Yeah, exactly. The result of this operation is always strictly smaller than n. Because, like, what does it mean that you take
Основной вопрос u одно и то же верхней точки, если там то внизу u прайм.
do you mean you should replace u by u modular n here?
Да.
Yeah. This is what you should do. Yeah, you should replace u by u modular n. This is the correct thing to do. Okay, now I want to add one property to the definition of a group. So this is the general definition of a group. But there is a special type of a group which is called an abelian group or commutative group. G is a group. It's called commutative or abelian. This is because of the surname of a mathematician, abelian. If the operation is commutative, so this is the property number 4, which says that the operation is commutative. I mean, the first term is actually pretty clear. So the group is commutative if the multiplication is commutative. And this is just the other term for this notion. So, for example, these groups and these groups are all commutative. Can you provide an example of a non-commutative group? Do you remember linear algebra? Who thinks that, well, he somehow remembers something from the linear algebra? Okay, good. You have several examples of non-commutative groups from the course of linear algebra. And these groups are permutation groups and general linear group. So let me give you an example. So GLN of, let's say, Q. What is GLN? Is the set of all non-degenerate square matrices of size n. So we take square matrices with rational coefficients such that the determinant of A is not equal to 0. So this is the set. And now, what is the operation? The operation is matrix multiplication. Now, we know that the matrix multiplication is associative, and the identity matrix is the neutral element. And we know that if matrix is not degenerate, well, first of all, the product of non-degenerate matrices is non-degenerate matrix. And for every non-degenerate matrix, there is a unique inverse matrix. So this is an example of a non-commutative group. This one is non-commutative. Okay. So what should be next? Oh, yeah, now I want to discuss the notation. You see, well, during the definition of a group, I use this special notation for the operation, which is like small circle. And when you deal with some specific operation, it's something like plus or multiplication or maximum or multiplication modular n or something like that. So there are, well, I mean, it's not very convenient to write circle all the time. And people used to two different ways of denoting the operation in a group. So let me show you these two notations. So there is a multiplicative and additive notation. But I think I should clear this part of the whiteboard because I need some space. So this is just a notation. There is a multiplicative notation and additive notation. Well, in case of multiplicative notation, the operation is just denoted like usual multiplication. And in additive notation, the operation is denoted like usual addition. It doesn't mean that the operation itself is multiplication and addition, because if G is an arbitrary set, it doesn't make sense. What it means that the operation is usual addition. There is no usual addition or multiplication on an arbitrary set. But it's very convenient to use like dot and plus to denote operation of the group instead of some strange symbols like circle or hash or something like that. Now, when we use this, well, usually this notation we use in case of non-commutative groups. And this notation we use in case of commutative groups. So this one is for non-commutative groups. This one for commutative groups. M means multiplicative notation, A means additive notation.
Commutative groups.
What again? Oh, okay. We use well, if we have a commutative group, we denote the operation by plus. Not by circle, not by any other symbol, we just denote it by plus for convenience. So if you open like a textbook and you see that you have a group and you have something like x plus y in your group, it means that plus is just the name of the operation and the group is abelian. That's it. This is just for convenience. So you can see that you are dealing with a commutative group. People just denote this operation by plus. Now, what are the other implications of these notations? Well, we have the neutral element. Well, the neutral element in case of multiplicative notation is denoted by 1. And in case of additive notation, it's denoted by 0. For example, it's like if you have matrices with addition, the 0 matrix is denoted simply by 0, not by this square table with zeros, just by 0. Or like 0 vector is denoted by 0, because like it's a neutral element with respect to the operation. And if you deal with a non-commutative group and you use multiplicative notation, you usually use this notation for the neutral element 1, because, well, you know, like 1 with the usual multiplication gives you nothing. I mean, it doesn't change anything. Now, if you have an element x, then and you want to compute inverse, if you want to denote inverse element of x, in multiplicative case, we denote it by x to the power of -1, and in additive case, we denote it by -x. So again, this is just a notation. So these and these are exactly the same things, but they are just denoted in a different way. And if you multiply x several times with respect to your operation, in multiplicative case, you denote it by a power of x, and in additive case, you denote it by x times n. So it doesn't mean that you have the operation of multiplication between integers and the element of your group. This is just the other notation for this thing. And the reason why this is the other notation, because if you consider an expression like this, x plus x plus x plus x, with n terms, well, it's convenient just to rewrite it as like n times x, which means that you just apply x plus x n times. So these and these are exactly the same things, but in different notation. Okay, yeah, this is more or less what I want to tell you about the different ways to denote the operation. Yeah, usually I will stick to the multiplicative notation because it works for every group, not just for not just for commutative. And in case of commutative groups, I don't know, I probably will also stick to the multiplicative notation. It doesn't matter. It's just a notation. And the reason why I'm showing you this notation, because this notation is used in the literature, so that's why it's worth knowing that what it means when people write something like that. Now, I want to give you a second definition. It's a definition of a subgroup. Okay. Now, suppose we're given a group G. And I want to define a subgroup of the group G. So I want to define H a subgroup. Again, following this pattern, the first thing I have to tell you what kind of data do I have. Well, the H must be a subset of G. This is all we have. Now, we have to pose some axioms. The axiom number 1, H must contain the neutral element of G. So the neutral element of G must be in H. The second axiom, H must be closed under multiplication. So if you have two elements x and y from H, then their product, well, their product belongs to G, but we want more. We want it to be inside H. And the third property, if x is inside H, then its inverse is also inside H. So if we have a subset of the group G, satisfying these three properties, then this subset is called a subgroup. Okay? And it's easy to check all these properties, like you should contain 1, you should be closed under multiplication, and you should be closed under taking the inverse element. Now,
G is a group или gigagroup?
is a group. Well, gigagroup would be nice, but probably later. Okay, now, what should I say here? Yeah, one remark. If you have a subgroup, you can provide it with the structure of a group in the following way. You see, if H is closed under multiplication, you can use exactly the same multiplication to define a binary operation on X, or on H. So because of the property number 2, multiplication from G can be restricted to H, and it's a well-defined operation on H. So now H is a set with a binary operation. Now, since this operation was associative on G, so it was associative for all elements from G. So in particular, it will be associative for all elements from H because we have a smaller set of elements. Now, since the neutral element of G is inside H, this will be the neutral element inside H. And since each element of H contains the inverse, each element of H will be invertible. So H with the restriction of this multiplication is also a group. So each subgroup has a natural structure of a group. Who was able to follow this? Are there any questions regarding to this? Okay, good.
When you say closed under multiplication, you mean under the operation?
Yeah, by multiplication, I mean the operation on the group G. So yeah, what I didn't say, when we use multiplicative notation, we call the operation multiplication, and in this case, we call the operation addition. It's just for convenience. Like, as you can see, I'm used to this terminology. Yeah, no problem. Yeah, by the way, here is an example of a subgroup. So if you have an example, if you have a group Z with addition, so this is a group, let's take the set of all even and odd numbers. So let's take H to be the set of even numbers, and let's say Y to be the set of odd numbers. So H and Y are two subsets of Z, okay? Now, is this true that H is a subgroup? Okay, yeah, because I mean, if you add together two even numbers, the result will be even. The zero element is inside even numbers, and minus even number is also even. So this is a subgroup. What about Y, the set of odd numbers? No. For example, the 0 is not inside Y, or the sum of odd numbers is even, so it's not closed under the operation. So there are many reasons why it's not. So this one is not a subgroup, this one is. Okay, we'll see a lot of different groups and subgroups, so I think this one example is enough for now. Now, I want to introduce you one notation in case of groups. So if we have a group, and we have an element X from the group G, we can raise it to the power of an integer. So it's easy to raise it to the power of a natural number, but now we can raise it to the power of an integer. So I want to define this where n is from Z. Well, for the definition, I have to consider three cases. The case n is greater than 0, the case n is equal to 0, and the case n is smaller than 0. When n is greater than 0, x to the power of n is just the product of x n times. This is it. When n is 0, this is the neutral element. And in case n is negative, we take the product of x inverse modular n times. So this is just by definition. So very natural definition, exactly what you expect. If you try to invent this definition by yourself, you would probably define it by in the same way. Now, we have some properties of these expressions raising to the power. So what are the properties? So the statement, if G is a group, then for every two elements of G, if you multiply them and take inverse, this will be the same as taking inverse of the elements and multiplying them in the opposite direction. The property number two, what is this? Oh, the property number two, if you have an element x from G, then what you can do, you can raise it to the power of -1 and then to the power of n. And this is the same as raising to the power of -n, and this is the same as raising to the power of n and then taking inverse. So these are exactly the same operations. And the property number three, if you multiply x to the power of n with x to the power of m, as expected, you will get x to the power of n plus m. So with this definition, these formal properties are satisfied. Okay, who thinks that all three properties are clear by the definition? Who thinks that we should prove at least something? The first one. Okay. Just in case, the proof of all these equalities will be given in the lecture notes, so even if I skip it here, you will be able to read them if you need. So the first one. Okay, so we want to prove this equality. Now, you see the element on the left is the inverse element to xy. So what you need to prove that this element is inverse to xy, okay? How can you prove that an element is inverse to something? Well, in order to prove that some element z is inverse to xy, you need to check that these two properties are satisfied. Then, since the inverse element is unique, any element z satisfying these two equalities will be the xy inverse. Now, what we need to check these two properties for this specific element. Let's substitute z by this element. What will we get? We will get this one. So this will be the first one. But in this case, you see, because it doesn't matter how to put the parentheses, you can cancel these two factors, and then you cancel these two factors, and the result will be 1. Okay? So, and in a similar way, you can check the second one. So we see that this one satisfies these two properties. So it's by definition the inverse to xy. Okay? Okay, just in case, are there any other questions regarding this statement? Should I prove anything else from this statement? Okay, so, I mean, I don't mind to skip some technical details, but it's better to ask you if I'm allowed to. Okay, what's next? Oh, next is definition of a cyclic group. Oh, yeah. I mean, there will be a delay. I believe I will end the lecture like in 15 minutes because there will be a delay at the beginning, if you don't mind. I hope it's okay. Sorry for this, but it's just for the first time. What should we give here? Cyclic group. Oh, okay. So, yeah, a cyclic group. So suppose G is a group. And G small is an element of the group G. let's consider the following subset. So by definition, so this is just a notation, and by the definition, this notation is the set of all integer powers of the element g. So this is g to the n, where n is in z. So just by definition, this is 1, g, g squared, etc. and so on. Here, g inverse 2, etc. and so on. So the set of all possible powers of the element g. Okay. Now, I claim that this subset is a subgroup of G. It's not just an arbitrary subset, but this is a subgroup. Okay? So, who considers that this subset is a subgroup? Yeah. The definition of a subgroup is here. Yeah, so, okay. Okay, so just in case, let me tell you explicitly why it's true. Well, first of all, we need to check that the neutral element is in our subset, but the neutral element is presented here because it's the zeroth power of our element by definition. Now, the subset should be closed under the operation, but because of this property, we know that the powers of one element are closed under multiplication. So the product of powers will be a different power. And if we take an element x, its inverse must be inside this set, but it's given here. If you take a power and its inverse, then this is also a power of the element x. Because of this equality, we have the third property. So this is a subgroup. And this subgroup is called a subgroup generated by the element G. So this is, let's say, the definition. It's a cyclic subgroup generated by G. Or as just, okay, let's say, okay, cyclic subgroup generated by G. In case G capital is equal to the cyclic subgroup generated by G small, we will say that G itself is a cyclic group. And in this case, G is a cyclic group. And in this case, G is a generator of G capital. So what does it mean that we have a cyclic group? Well, when we have a cyclic group, it means that we can find one specific element in this group G, such that all other elements are just powers of this chosen element, and that's it. And these are all possible elements. So, in particular, it's clear that G is not more than countable. Okay, so what should be next? An example, as usual. So let's start with a simple case of a group, Z with addition. So this is our group. We know that Z with addition is a group. Let's take the element 1. What is the cyclic subgroup generated by 1? No. But what is the power of 1 in case of Z with addition? Yep, exactly. This will be Z itself. Because what are the powers? I mean, in this case, what does it mean that we have a power? The power means that we either apply the operation to the element several times, or we'll apply the operation to the inverse of the element several times. In this case, if we take, well, actually, in this case, we use additive notation. So the power of 1 is actually n times 1. Yeah, and I mean, it's pretty clear that it will be exactly the same. So in this case, this is what? Neutral element in 1, the second power of 1 is 2, the third power of 1 is 3, etc., because it's 1 plus 1, 1 plus 1 plus 1. And in case of negative powers, we have minus 1 is just the inverse of 1, then minus 2 is minus 1 plus minus 1, and so on. So yeah, this is the set of all integers. So in particular, we see that the set of integers is a cyclic group, and 1 is a generator for Z. Is there any other generator? For Z, yeah. Yeah, exactly. So if you take minus 1, you will get exactly the same result. And these are all possible generators for Z. If you take any other integer, you will get a smaller subgroup. For example, if you take 2, what is a cyclic subgroup generated by 2? Yep, this will be the set of all even numbers. So if you take 3, this will be the set of all numbers divisible by 3. Well, you can simply denote it by 3 times Z, so like 3 times any integer. Yep. So these are examples of cyclic subgroups, and this is an example showing that Z is a cyclic group itself. So what should be next? Oh, yeah. What about this example? The real numbers addition. Is it cyclic or not? Why?
Because it is impossible to obtain some fractions.
It's uncountable. Yeah, exactly. Yeah, it's uncountable. So is not cyclic. Okay. Okay. Let me give you another definition. Is a definition of an order of an element. Now, again, G is a group, and we're given an element G small from G capital. Now, I want to define an order of an element G. So what is this? Well, now, what you should do, you take G and start multiplying it by G. So you multiply G by G by G, etc. And you stop at the first moment, you will get 1. And this is the first time you encountered 1. Then, in this case, the order of G is n. So this is the least amount of factors such that multiplying G n times, you will get the neutral element. So in this case, the order of G is equal to n. Why do I have a second option? Yeah, because what may happen, you will never get 1. So in this case, you say that the order of the element G is infinity. That's it. Okay. What is the order of 1 here? Well, the element n must be at least 1. I mean, why 1?
Because if we multiply it,
Why multiply?
oh,
Infinity. Because, again, let me show you. So the neutral element here is 0, okay? So let me reformulate this in case of z plus. So we take element x and we add it n times, where n is positive integer, and we should get 0. Okay? So we add element x n times, and we find the smallest possible n such that the result is 0. Let's take x to be 1. In case of 1, if you add 1 several times, you will never get 0. Okay? So the second option, what happens here, and we have the order is infinity. So the order of 1 is infinity in z plus. Now, what is the order of 2? It's infinity. And actually, every element but 0 has infinity as its order. Okay? And what is the order of 0? It's 1. Yeah, because if you take a neutral element, exactly one neutral element is equal to neutral element. So the order of 0. So the order of 0 is 1. The order of any non-zero element is infinity. This is what happens in z plus. Okay, and now I'm going to formulate another claim, but I believe the proof will be during the next lecture. Okay. Yep.
I need and like n as another. Why don't we say like true or false, basically?
Because there are other options. There are groups where the order could be any integer number. For example, if you take Zn with addition, then the order is always finite number, is a divisor of n. Yeah. Yep.
And why do we compare to 0 when we count for x equal to 1 and to 1 in definition?
Oh, because in the definition, I use general multiplicative notation in a group. Using general multiplicative notation in a group, the element 1 refers to the neutral element. So if you want to apply this definition to a specific group, you need to replace 1 by the neutral element of this group and the multiplication by the operation of your group. So in this case, the operation is plus, so you replace multiplication by plus, and neutral element is 0, so you replace 1 by 0. I mean, this is a general pattern. Okay? Good. Yeah, this is somehow confusing. I use 1 like as an element is in all the definitions, and then you somehow have to switch it to something else in a specific case like z plus. So yeah, and the reason is because this is like a general notation for an element, and it's a bit confusing. But you know, I told you already that algebra is the best way to make fun of students, and what is the best way to make fun of students is to make them to be confused. And what is the best way to make you to be confused is to use like 1 million different ways to denote the same thing. So I denote 0 by 1, 1 by 0. That's just magic.
Sorry, we lost the confusing students. I think Chekhov is
Okay, so let me formulate the final claim. Okay, the claim. Suppose, what should I say here? I want to classify, okay, yeah, I want to classify all the cyclic groups. So suppose I have an element of a group G, and this is a group. Now, I want to describe all possible cyclic groups generated by G small. So I want to know the structure of this set. And what happens, there are actually two options. Let me write, okay, no, I'll write it like this. So there are two options. The option number one is when the order of G is infinite. And the option number two is when the order of G is finite and is equal to n. Well, in the first case, all these powers are different. In the first case, we will have, let's say it like this. So G m is not equal to Gk if m is not equal to k. So if the order of an element G is infinite, it's impossible to have two different powers to be the same. They're all distinct. So you have exactly countably many elements. And in the second case, you have exactly n different powers. In this case, you have exactly n different powers. And if you want to choose all the powers representing all the elements, it is enough to take the powers from 0 to n minus 1. So these will be all distinct powers. So first of all, any power is equal to one of these ones. So if you take like G to the million, it will be something, it will be equal to some of these ones. And all these ones are distinct. So there is no repetition here. So this is the structure. Okay, there is a question. Yep. Yeah, that's just by definition. That was a part of the definition. G to the 0 is the neutral element. Okay, so this is the structure of a cyclic group. So if you, if you have a cyclic group, a group generated by one element, so you have only two options. So this group, so either all elements, all powers are completely different. So it's easy to deal with these powers. There is no repetition, like each element is completely determined by the power itself. Or you have a second option. You have finitely many distinct powers. And in order to describe all the powers, you can choose this segment. And these are all possible powers, and they are distinct. And these two options can be distinguished by the order of the element G. So if the element G has infinite order, so then this happens. If it has finite order, then this happens. And as you can see, for example, here, the element 1 has infinite order, and all the powers of the element 1 are all integers. So it works well. Yeah, the proof will be during the next lecture. I think that's all I wanted to present for you today. Thanks for being here. I hope you will come to the next lecture. Thank you, guys.